Well, good afternoon. It's always a difficult challenge doing a session right after lunch, so bear with me. I'll try to keep my energy up. My name's Eric Schmidt. I'm the product manager for Google Cloud Dataflow in the cloud platform team at Google. That's my email address, cloudy@google.com. If you want to send me questions, etc., feel free to email me. My name is Cloudy because the other Eric Schmidt is taken, and he has a lexical condom, if you will, around all things that are Eric Schmidt derivatives. So, true story. The goal of this talk really is to help you understand Cloud Dataflow and possibly draw some conclusions to existing data processing models, which I know we are all exposed to over here. This is the whole purpose. And hopefully we have some fun along the way. If you have a burning question, raise your hand. I'll attempt to answer it, or I'll address it after the session. The title of this talk is about two worlds becoming one, and it's actually four, but I couldn't figure out a way to creatively create the title. So here you go. This talk is around one concept of basically taking the promise of the cloud and fusing it with big data. In many ways, big data technologies have not fully exploited the promise of the cloud, especially in terms of elasticity and on-demand computing. I'm going to talk to you about how we're helping solve that problem. The second thing that I'm going to talk about is, today most of us live in a batch or streaming world. How many of you get paid to write MapReduce code or run Hadoop clusters running MapReduce jobs? How many of you get paid to run Spark or Storm clusters? Okay. One of the challenges that we see in the marketplace today, especially with a lot of the customers that we have, they're basically living in these two different worlds, and they're having a difficult time reconciling the architectures and the costs involved to manage both. So this is what the talk is really about, basically kind of taking these two different worlds, if you will, and merging them together where logical and driving some optimization. Throughout the talk, I'm going to use this example, basically referring to this concept of time to answer. At the end of the day, most big data challenges are all about how fast can you answer the question. There's three different types of questions here. On the right-hand side, I have a very, very batch-oriented job scanning over potentially terabytes worth of data. In the middle, I have a quasi-real-time, quasi-batch job that's looking at relatively a month's worth of data, but it needs some type of enrichment to the data, some correlation to another data set. And the last one is a true real-time streaming implementation, something that maybe your boss would say, hey, I want a real-time monitoring system so I can understand real-time traffic. These three questions have fundamentally different architecture implementations to answer them. I have a little demo that's effectively running at around 4,000 to 5,000 events a second that I'll show you a little bit later to answer some of these questions. Now, to answer those three questions in some sort, this is typically how things are built today. You have some type of edge ingestion system that has some elastic capabilities. On Google, we have App Engine. You may be running on EC2 with some type of container model, et cetera. But then from there, you're typically forwarding messages in some type of publish-subscribe system, whether it's Kafka, RabbitMQ, et cetera. And then you go ahead and fork the stream. You have your batch jobs running in Hadoop. You have your real-time streaming running in Spark, that inside of a managed Hadoop environment or separately, and then you're pumping data back into some type of engine in order to process it from a SQL perspective. Replace Cassandra with Mongo, et cetera. But you fundamentally have two different systems running. This is the Lambda architecture. And in many cases, this is a fine architecture to implement. But if you take a step back and start thinking about time to answer, depending on what type of architecture you implement, you have this tension and polarity around four concepts, which is speed, how fast can I run? If you're running in in streaming mode, how accurate is my data? Right? In streaming mode, you're never guaranteed to have all of your data. And in some cases, you might not even know that you don't have all of your data. So if you're running as fast as you can, you want to answer questions, and you don't have all the data, accuracy becomes a problem. If you're running as fast as you can, and your boss comes in and says, I need that question answered twice as fast, what do? We typically go deploy more infrastructure, costs go up, complexity goes up. So there's this constant tension between, hey, at the end of the day, I just want to get answers faster. And depending on where you're running these jobs, typically elasticity is not your friend today. at a macro level. Some things to think about. Time and life never stop, especially in streaming mode, right? Data just keeps on coming, keeps on coming, keeps on coming. The data sets and schemas that you have, even though we're all great developers and we think we can create rock-solid serialization, deserialization mechanisms to handle variances in schema, but the reality is something's going to change in your system. Or you're going to have skews in key structure flowing through your system. The third point is the scaling models today, they're not static. At the top, we all like to live in this world. We'd like their business to keep growing and growing and growing. But what happens if you're sleeping and you're wildly successful and you had growth and you had a big burst overnight, but you didn't have an elastic system to deal with it? So what do? Well, we go ahead and build to peak, or we basically build to peak where we think we could have a maximum burst. And at the end of the day, there's a lot of wasteful compute left over in this model. And if you don't have it, it can create lag. So that reinforces the 4 tension points I was talking about before. So the question would be, well, what happens if you just had a simple knob for speed? Like you could stop thinking about how you deal with accuracy, how you deal with cost as it relates to complexity, right? So, effectively, this is what we're doing with Cloud Dataflow. We're providing you one simple environment to focus on, which is basically speed. But we're also giving you the ability to control accuracy, because you still have to deal with it, but we're helping you deal with it in a very fine-grained way, as well as providing you with intelligent resource elasticity to help you optimize job run times. How many of you have heard of Dataflow before? Just a couple. Great. So this is what it is. It's really 2 things. It's a collection of SDKs that you will end up using to build batch or stream-based parallelized data processing pipelines. So you have a set of SDKs. Think of complementary things like Crunch. You express how you want your data processing pipeline to operate, and then you go ahead and submit your pipeline to the Dataflow managed service, and we will handle the execution and optimization of that pipeline for you. These are 2 separate things. Where could you use Dataflow? Really comes down into 3 categories, and really the first 2 are the areas where we see the most uptake. If you're doing traditional batch ETL, so for that first question, and you have a ton of data, you have terabytes worth of data sitting in HDFS or S3 or GCS, et cetera, and you want to move it someplace else to do interactive analysis, great. Create an ETL job, suck up the data, do some transformation, do some filtering, do some enrichment, push it into your other store. At the same time, you could also do batch computation, classic MapReduce style, where I'm going to take and compress down data into some type of logical batch computation. Or you could use it in streaming mode to do continuous computation. Point data flow at a stream and continuously compute on top of incoming data. And the last you can do with it is you can basically orchestrate different jobs, where you can basically have one data flow that's operating on a certain stream of data that will kick off another data flow, et cetera. The benefits, I'm trying to clear all this stuff out before we get into the technology. It truly is a no-ops model, modulo the knob that I was talking about. Resources are allocated on demand. You want to run a job, you submit a job, we allocate the resources for you, we manage their lifetime, we have intelligent auto-scaling to help optimize where we can to add additional resources. And we also do this concept of automated work optimization, which I'll talk about later, because that means, hey, we can add more resources to the system, but are you really getting your bang for the buck? Are we exploiting every CPU that we possibly could in order to answer the question? The second benefit, it's a unified programming model, which you'll see in a minute. It's one programming model for batch or stream. You don't have to worry about, well, I'm in the MapReduce semantics or am I in stream-based semantics? One programming model. Today, the other aspect of this is that the programming model itself is open sourced. We made this decision from the very beginning. It's on GitHub. We have a Java 7 implementation today. We have a Python 2 one on the way. We've had a lot of feedback from people for a native Java 8 implementation to exploit Lambdas. We heard you. We're working on it. As a result of open sourcing this, the community has done interesting things, like build a Scala implementation for the SDK. You like the service, but you don't like the Java 7 implementation? Fine. wrap it with a different language. Or you like the programming model, but you don't like the managed service. The folks over at Cloudera, Josh Wills, he took the SDK and built a Spark runner for the Dataflow programming model. So express your pipeline in Dataflow, run it on Spark. And our buddies over at Data Artisans, driving Flink, they did the same thing. All right, so the kind of benefits of the open source model is you can extend it as you wish, from a programming primitives, or if you want to run on alternate execution environments, go for it. So release timeline. We came out to the world last June, at the end of June, and said, hey, we're building this thing called Dataflow. That was EAP. Alpha was right before Christmas. And today, I'm super happy to announce that it's open to everyone in beta, effectively 7 minutes ago. So go rock. Yeah, yes, thanks. The next milestone is GA, and for all the math majors in the room, if you look at the delta between June to December, December to 8th, go ahead and build some type of predictive model on when we're going to release GA. So that's Dataflow, but I want to take a step back up and talk about Google as a platform for cloud. I'm not going to get into all the details of it. We have all the kind of basic infrastructure services that you would imagine. We have standard IaaS support for compute, for storage, for networking, et cetera. And then we also have managed services for big data, of which Dataflow is a member of that family. We break big data at Google down into 4 categories. Capture, right? Think about all the IoT scenarios. Storage, both for short-term as well as long-term. Processing, and then analysis. And Dataflow falls into the 3rd category. Taking a step up, back into those bubbles, Dataflow is really kind of best friends with these 2 other managed services, as well as with the rest of the open source community. So from a managed service perspective, Dataflow is highly integrated with Cloud PubSub, which is a globally available messaging system. No sharding, no concept of regions. You basically say, I want a queue, specifically a topic. I'd like to put data of this type into it, and I can have one-to-many subscribers. Done. I write data into the topic. It's ACT. It's globally available anywhere at high 5 digits QPS throughput. Dataflow we're going to dig into more, and BigQuery is our interactive analysis engine. Capable of ingesting data at hundreds of thousands of events a second. Right now, we're doing around, I think, 150 to 200 terabytes worth of ingestion a day just in streaming, and probably quadruple that in terms of standard batch upload. So we're talking massive data sets that are being used and queried by BigQuery. So back to time to answer these questions. Well, you could do it this way. This is perfectly valid. We have lots of customers that are doing this today. It's like, hey, I kind of like Dataflow and BigQuery, but I'd like to use Kafka because I have an investment in it. I know how it behaves, et cetera. Great. We have an extensible input and output or source and sink model for you to extend the Dataflow to other source environments. Or you'd say, well, I don't necessarily like BigQuery. I'd like to write to Cassandra or to Mongo or to Couchbase. Awesome. You can do that. Or, hey, you don't like the managed runtime? Go ahead and use the SDK, slip in Spark, express your pipelines in Dataflow. Also a completely valid environment. What I'm going to do quickly is show you this, basically the world of what it would look like in a completely no-ops world. So the demo I'll run through quite quickly is I'm going to create a data set to ingest some data. I'm going to create a globally available queue, and I'm going to submit a job. And actually, I already have one running, so I'll kind of walk through quickly what that is. The scenario that we're going after is I want to calculate in real time how many users are on my system on a per-minute basis. Fairly simple question to ask. I also want to shuttle all of my input data into BigQuery as fast as possible. Basically, I want to archive it. This is a real classic problem that whenever we're talking to customers, they're like, I want to answer a very specific question, but I don't want to throw any of the data away, and I'd like to be able to query that data with 0 latency. Like, all right, great, awesome. We'll provide unicorns for you too. So, I'm going to get into the demo a second just to clear this out. So PubSub, we talked about it being globally available. You have this concept of topics to subscriptions. You basically publish a topic, you publish messages into it, and then you can have one-to-many subscriptions pulling from it. We have auto expirations. You can basically age out data, which is really nice for big data scenarios where you want to do replay, et cetera. Low latency, we're talking about on average around 200 milliseconds or so to write into the system. We're working on a native socket implementation to drive that down. We got a lot of feedback from people like, hey, this is cool, but I need 50, 40, 30 milliseconds. Working on it. BigQuery, we talked about this already. Highly scalable. And another announcement that we're making today is that BigQuery is now available in our European data centers. We have 2 European data centers, so that you can exclusively manage, control all of your data inside of those 2 data center locality. So this is a great data sovereignty story. Same thing applies if you're running operations in the US. You can use this feature for that. We also introduced new row-level security and data expiration as well. So you can imagine I'm ingesting a bunch of data, and I just want it to age out, log files, et cetera. Cool. So let's flip over. Awesome. So this is Dataflow. This is one view into Dataflow. This is the live pipeline that's processing this data. The data is basically fake health data coming from a video app player on phones. And the function of this job is to do 2 things. I'm going to read data in from PubSub. I'm going to do some data transformation on it, convert it from a string format into a Java object that I'll do some analysis on top of. And then I'll go ahead and do some additional processing, and I'll ultimately pump it into BigQuery. And at the same time, I'm also splitting the graph and doing some ETL cleanup on these raw records, and I'm writing them out into BigQuery. So I've been running this thing for about 3 hours or so. Let's see, it's processed around 48 million records, so not bad. Let's go over and see how things look. So if the demo gods are happy with me right now, it is currently 12:57 UTC. So we just wrote out the last window, so the last minute, and we are roughly, we're around 3 minutes behind live right now on our windows. On our ingestion, let's see, the last timestamp for here. This is querying over several hundreds of millions of records, so give it a second. So the last one that came in was at 12:58. So, okay, great. So I was able to answer these 2 questions. And keep in mind, this pipeline will keep running in perpetuity. I could leave this thing running for days, and it's just going to keep reading. All right. Oops. We'll get back into more demo and code in a minute. So let's talk about how you'd go about building a flow, whether batch or stream. On a weekly basis, we push the SDK to GitHub. We also take pull requests on a weekly basis. If you successfully get a pull request through us, we'll send you a bottle of champagne. So we've had a bunch of them, but it's a lot of fun. And then on a monthly basis, we push to Maven. So actually, just this morning, we pushed a new build of the SDK to Maven. Specifically what the SDK does, this is kind of logically, looks like my slide got screwed up, but logically, you end up building a pipeline. The wrapper of the pipeline has at-once guarantee processing of data, modulo completeness thresholds. What this means is if the data enters the pipeline, we will guarantee that it is processed. In batch mode, if there's some type of exception in processing the data, we'll attempt several times. You can control how many times we attempt to do it. If we finally can't complete processing that particular record, we'll fail the job. Some differences, we only re-execute just that small part of the DAG. So if you have a really, really big pipeline, we're only just reprocessing that one particular element inside of the DAG related to that piece of data. In streaming mode, this is, I say, modulo completeness thresholds. You may tell us up front, hey, if you have late arriving data coming into the system, I don't want the pipeline to process it. So there's the outer pipeline. First thing you do is you specify a set of inputs. We can ingest one-to-many types of data. In this case, I was pulling in from PubSub. You can imagine pulling from GCS, S3, HDFS, et cetera. And you can have multiple inputs into your pipeline. From there, you then specify a set of things that you'd like to do. What would you like to do to the data? So you can specify a set of transforms. These are common things like aggregations, filters, joining, et cetera. And the next thing you do is you express the what onto a where, some type of time space. We have time space of fixed windows, sliding windows, sessions. If you don't like our time space, you can create your own. The sessions one is pretty cool. You can tell us this is what the beginning of a session looks like, and this is what the end of a session looks like. Clickstream analysis, an example. So if I see a new user come through that I haven't seen in a couple hours, I'm going to start a new session. And you tell us, hey, if you don't see that user for 5 minutes, end the session. So you have who, what, where, and then you have when, which is this concept of correctness, which is as your windows are processing, you tell us at what level of watermark tolerance you would like to emit data. And you do that through triggers. And I'll talk about that in a minute. And the last thing, if you wish, and I think in most cases you want to output data someplace else. The same concept as applies for inputs. We have a whole series of outputs that you can use, and you can mix and match them. You can have multiple inputs, multiple outputs. So this is the Java 7 implementation of the pipeline that I'm running right now. This one is running in batch mode. So I have a pipeline. I create an instance of it. I tell it to begin. I say, hey, text.io transform. I want you to go read from this URI that I cleaned up so we don't have a bunch of ugly code. From there, I have this thing called P collection, and then I pass it through a series of transforms, and I'm done. There's more code to this, but effectively, this is the root of the pipeline. So we talked about P collections as the thing that gets materialized first in the pipeline. Let's talk about what those are. It's a parallelized collection of type T, and I like to say that it's the hippie cousin of an RDD, because a P collection can be of any type, of any size, and we end up optimizing the pack or bundle of data that's inside of the P collection. The P collection may be bounded or unbounded. You could say, I want to read from HDFS, and I have a bounded source, or I want to read from Kafka, an unbounded source. You can also create them in memory. A good example would be, maybe you have some input data that you want to use for a training set. It's a couple 100,000 records, and maybe you build that on the fly with some code. You can do that as well. And these P collections ultimately often contain key value pairs, things that you end up doing some type of group by and or shuffle with. So that's a P collection. All right, so now I have this virtual parallelized collection of data. I want to do something to it. You use a SDK primitive called a parallel do. And what it does is it will take a n number of bundles that represent your P collection and process each one of them. So you can imagine if you had 100 workers spread out in your cluster, they would all have 100 different instances of Pardews running through parallelized split of your P collection. And this corresponds to the map and reduce phase in Hadoop. You basically have Pardew and then you have a Pardew and then a group by key. So then we have group by key. You ultimately want to do some type of shuffle and emit a reduced set of data. We have a built-in primitive for that. And the main question here is, hey, wait a minute. How do you do a group by key on an unbounded collection of data? If you have a stream of data that's continuous and you want to do a group by, well, you have to know where to basically split the stream. Which are windows? Right? So basically, you can logically divide up the output of your data into fixed windows, hours, et cetera. If you don't like this time space, you can build your own. One of the things that I absolutely love about this product is you can create windows that are either tied to arrival time from your processing system. So in the Kafka space, you're reading from Kafka. You process data based on the arrival time that you're pulling data from Kafka. Good use case. You may also have another use case where you want to process the data based on the actual event time, the actual clock time that it happened on the source. So you can get finer grain accuracy on what was actually happening with your system. So you can kind of pick and choose what you want to seed as your time input. So managing correctness, which I talked about at the beginning and then in the SDK. Kind of two things to wrap your head around. One, the system itself, the service, and then the SDK service. The SDK surfaces this concept of a watermark. So the input system into Dataflow can instruct and or give some hints to what it believes to be the oldest unacked message in the system, right? So if you look at the graph, and basically this is clock time, but then this is the logical time of data that's being received. You know, that wave will never be linear in the real world. You will always have some type of lag. You know, the example I use all the time is, say you have 1,000 edge web machines that are all handling traffic, right? And one of them tips over, and there's a couple 100,000 web logs sitting in there. Well, you know, you being a smart developer, you had some type of containerization mechanism. You're able to turn that machine back on in 45 seconds, a minute, et cetera, and boom. Now you have 100,000 logs all being plowed into your data processing system. And then you ask the question, well, like, am I going to process on arrival time, or do I want to process as those events actually happened? So that's the concept of a watermark. The way that you express correctness in the system is that you then apply this concept of a trigger, and there's some sample code here, to the window that you created. And this one's kind of cool. So the way that this trigger reads is I'm basically saying after I receive my watermark, I want to repeat forever the following steps. Once I get an additional element in my window, and now we shrink them down to panes, first element in a pane, I want you to wait 10 minutes. And then after 10 minutes, I want you to emit a new window. So using the use case, you know, web server goes down, you wouldn't want to emit a new window, you know, for 100,000 of late arriving messages. So in this model, we basically say, hey, go ahead and wait till you get the first one, and then after you get the first one, wait for 10 minutes, and then emit the window. And this use case is kind of exaggerated. Basically, I want to continue to do this for 2 days, right? So this would accommodate for 2 days of late arriving data. In the weblog example that I use, probably a couple hours is okay. So you can chain these however you want. What's not on this slide is the type of data that we then release to the window. We run in basically 3 different modes. We can release just the data that's arrived. We can also hold on to all the data within that window and say, hey, here's all the data within that window, plus some new data, plus some new data, plus some new data. Or we could also subtract data from that. Say, hey, here's all the data that was in the window. Here's some late arriving data. We're going to move something else out of the previous window. So that was correctness. And then we get into composite transforms. You know, this is really where the SDK starts helping you. And we get lots of feedback from people like, hey, we like your composite transforms. We'd like more of them. So we hear you loud and clear. But these are things like doing basic counts, removing duplicates, joining data, min, max, sum. So count is just a wrapper of pair all the data with ones, do a group by key, and then sum all the values. So that's high-level SDK. Let's get into the service. How did I get that job running? On the left-hand side, you have your code. You're going to submit your code over to the service. The first thing that the service is going to do is optimize it. We're basically going to fuse all of those parallel operations down to the fewest number of operations and fewest number of shuffles. From there, we go ahead and push out all of the compute infrastructure that you would initially need to start the job, we go ahead and push your code to all those workers and start executing work, right? Whenever it's done, all the workers go away in batch mode, and you're finished. All those resources are decommissioned. In the meantime, whenever they were running, all the workers are emitting information back, so then you can see progress like this. Or you could dig into all the job logs. So that's the service. I'm going to quickly spill over this. You can read the slides later. A lot of people ask, hey, what do you do for graph optimization? We do a lot. We could have a 3-hour session on this. These are the high-level ones. Obviously, things that are consuming and producing the same data, we fuse those together. Siblings that are operating off of the same P collection, we fuse those together. And we also do some other things, if possible. We call this combiner lifting. If at some point in a Pardue we can pull the aggregation up instead of having it being done at the shuffle level, we'll pull that back up into the Pardue. There's a Flume Java paper that was released a couple years ago that talks about the majority of our optimizations in detail. So lifecycle management, what happens? Whenever you start at time 0, we basically deploy a fleet of machines. We schedule and monitor them. If a machine's having health problems, we take it out of the pool and put it back in. Table stakes, right? But the next thing we do is we can also intelligently autoscale the pool. So we start with 12, and we start pressure testing, and we look at the overall throughput, and we'll add additional machines to the pool. We'll keep adding. And then at some point, if we basically say, hey, we have diminishing returns, we're going to pull resources out of the cluster. This is a classic example where I have a steady state of data, and basically whenever I get into here, I have some really, really complex computation and or shuffle, and then I have a small amount of data that needs to get written out to a data source. So a lot of resource saving in this model. This next concept is about work optimization. These are actual memes that were posted inside of Google over the past couple years as it relates to stragglers inside of a MapReduce job, right? Yes, we use MapReduce just like everyone else. Well, a lot of people now use Dataflow. But this concept still exists, whether you were in MapReduce or in Dataflow before we implemented this feature. You go ahead and submit your job, you're running like, hey man, I'm cranking, and then you're like, wait a minute, I have 1 shard or 2 shard that's just completely backed up, and I don't know why. My key structure has gotten completely skewed. I had a new piece of data type that is interacting with the system in a way that I never anticipated. So we introduced this concept of dynamic work rebalancing, where we're constantly monitoring all the resources within the cluster, and we're looking at their overall throughput. And we compare them to all the other resources that are processing like work. And if we see that they're starting to lag behind, we will dynamically pull work away from that worker, rekey, and give a worker that has some unused resources the opportunity to do that work. So this is an actual job timing that we did a couple weeks ago. The effective clock time without rebalancing was around 100 minutes. Turn it on, same exact cluster size, save around 35 clock minutes. So, kind of if you take and fuse these two concepts together, dynamic work rebalancing and autoscaling, then you have a system that can heavily, heavily exploit the compute resources needed in order to answer this question in a timely fashion. So here's the kind of the promise of the cloud, kind of pulling back up. We have invested. This is now probably year 14 of innovation around big data. We're also investing heavily into the cloud. At the same time, in order to build these managed services. And at the same time, I don't want this to be lost on anyone, we are continuing to embrace all types of open source workflows on top of GCP. You want to bring your Hadoop workloads to GCP? Great. We're continuing to optimize our infrastructure, GCE, storage, et cetera, to run Hadoop-based workloads. At the same time, we're also continuing and spending a lot of innovation time to build fully managed services. And this is where the optimization comes in. Things like dynamic work optimization, auto-scaling, etc. So if you take a full step back, this is really what Dataflow is about. You think about resource provisioning, handling hardware scale, reliability, deployment and configuration. I mean, this is real stuff. The graph may be a little overreaching, right? You still have to monitor your jobs, et cetera. But we're truly pulling the majority of the ops aspect out of the equation to help you spend more time, hopefully, writing more code to answer more questions, or just answering them faster so that you can get on to the next problem. So let's get back to the code. Let's see if this thing's still running. Demo gods. Where are we at? All right, so we basically caught up while I was yakking away. The last timestamp in there was 13:15. So yeah, we're still about 3 minutes behind live. Take into account, on my Windows will always be a minute behind. Data throughput's probably around 15 seconds or so writing out. So we're a little laggy today. But let's go deploy a job, and then I'll answer some questions. How many cores do we want to use to run this job? Throw out a number. 42? It's too small. Something higher. 100? 200? Okay, cool. It was 40? Okay. We'll do this. I'm going to turn auto-scaling off just for the heck of it. And whenever I hit go, it is going to take this code, the code that I showed you. So this is the outer code. I'm going to go into session analysis. Let me increase the font size here. Right? This should look very logical to you now. Right? So I have my outer wrapper. This is where I'm calculating session. So basically, events come in. I want to key them. I want to window them into a fixed window of 1 minute. There's the triggering code that I showed you. It's turned off in batch mode. And then I have my output. So what am I doing? I'm going to remove some duplicates. I'm basically going to combine all these and count, and then push them out to BigQuery. So this exact same code, modulo these triggers, I turned them off just for the sake of the demo. It's the exact same code that's running in streaming right now, except we're going to turn around and run this thing in batch mode. So run on service, I turned off auto-scaling, 200, go. So right now, what it's going to do is it's going to compile. It's going to perform a set of pre-optimizations. It's going to upload the code to the service. So we're over Wi-Fi right now. Come on. There we go. There's the version of the SDK. There's all the optimizations that got fused away. So there was a ton of fusion. This basically gets fused down to one major stage. And I'm starting my worker pool. That's good news. Let's go back over to Dataflow. Go to all my jobs. There it is. Questions?
How do you manage your, I'm assuming, is it a free service or not? You need to enter your credit card.
Or cash, either one. So, yeah, so all the services on Google Cloud, similar to EC2, et cetera, they're all managed through some type of resource-based, pricing model. So right now, in order to run Dataflow jobs, you pay for two pieces. You pay for the compute and additional resources that you would use, so compute plus a BigQuery for that job, and then you pay a surcharge for the service, and it's both of those, in almost all cases, they're all calculated based off of time. And in the docs that we just released a couple hours ago, you can go read the actual model. So But the pricing model is a function of time and cores. So.
For the stream processing, what kind of processing guarantee that Dataflow provides? Is it at least once or exactly once? Or
for stream, it's at least once, meaning, well, so at least once modulo your correctness. So if you say that you would like to drop late arriving data, that data will never get in. If data comes into the system, we must be, I don't know if we're not connected to the network here. If data gets into the pipeline, we will guarantee processing in streaming mode up to the point where our retry logic fails, and then we will kick it out of the pipeline, but we'll keep running. In batch mode, we fail the job.
So if you're aggregating counts, there can be over-counting, essentially?
No, for the actual step, if you're using our implementations, for that actual step, it will remove from the count.
How does it work? If you're using at least once, how does it take away duplicate counts?
It will basically subtract whatever action happened within that transform.
BigQuery will subtract, or the
no. The actual step itself.
Okay.
Yeah.
And for to actually use it, if your Kafka cluster is outside of Google, would it still be can you still connect your Dataflow to a Kafka cluster sitting in Amazon?
You could. I think that would probably be cost prohibitive on both sides because you're going to pay for egress out of EC2 and you're going to pay for ingress into cloud.
So you have to have a Kafka or the PubSub system on Google.
Yeah, it's really just going to come down to data locality. Like if you can get your data into the network, then that you won't be charged.
Okay.
So. What else? Yep.
So I have just two questions about the programming model for the SDK.
Mm-hmm.
Is it using the reactive programming paradigm?
So the question was, are we using reactive programming model? No, right now. Yep.
Okay. So and for the optimization step, how did you catch the non-blocking operations? So sometimes we have operations that are not blocking for the stream, so you can just execute them on separate thread or something like that.
So the question is, how did we account for non-blocking? If you, this is probably a better one to take offline because I can kind of walk through the scope model of whenever you're inside of a Pardue, we optimize and ensure thread safety there. If you're trying to do some globally available variable, there's a different model to do that than typically how you would implement. So basically, we have global available data that you can share in a thread-safe way across all the workers. Yep. Yep.
MapReduce is actually like a water flow. One job needs to finish, create some files, and next job can run over again using the files from the previous job.
Yep.
So you mentioned this like pipeline. Can we pipeline different operators or programs or jobs or whatever it is to create a pipeline that is continuously processing?
Yeah, so there's two things that you could do. You could have multiple MapReduce jobs inside of one flow. That's one thing you could do. Or you could separate the processing physically across multiple pipelines and have the output of a pipeline trigger the next pipeline to start.
So it's still like a water flow. I mean, you can have pipelines in parallel, but they need to finish for the next to start.
Yes. Yep. Yeah, okay. And this is part of the fusion process. If we see that we can get your data into one common shuffle, this is a challenge of having all these discrete MapReduce jobs. In certain cases, you could actually fuse them down into one common shuffle. So. Yep.
Related to the gentleman, he's stating the first job needs to finish, but as I understood it, you can actually have data arriving late and adding to the flow again?
Yes. So
it doesn't necessarily need to finish before you can continue, does it?
No, and here's an example. Like I just went back to my development environment. I'm going to submit another job. You can submit as many jobs as you want, run them in parallel. All the jobs are running simultaneously. Yep. But if you wanted to use a job as a signal for another job, you could also do that. And oh, by the way, my streaming pipeline is still running, right? So now I kicked off those 2 batch jobs. And if I go back, I think my streaming pipeline is, yeah, it's down here. So this guy's still chugging away on input data from PubSub. Yeah. Yeah, one more question, and then we're done. And I can hang out outside, too. So.
Monitoring and auditing for errors. How I will monitor the system?
So there's 2 ways to monitor it. Through the monitoring UI that I showed you, we also have a command line interface that exposes all the job information and job statistics, so you could pull them out from an API perspective, maybe pull them into Mbari, put them someplace else. We're actively working on better surface area so that you can integrate the data into other monitoring tools, but today, effectively, you have the monitoring UI that I showed you, and then you have a command line interface that you can ask for all the events and counter information for the job. Yeah, and the other piece to that is all the logs for every job are all pumped into a common logging environment. You don't have to go schlepping through instances to figure out what's going on. They all get merged into one logging environment. So, cool. Thank you. Take care. I'll be outside if you want to chat.